using electrical and electromagnetic methods. And now I have this short presentation about controlled source of magnetic fluids survey. This is a map where the area is located. It's in the north of Mexico, in Sonora. The area is between Nogales and Cananea. And this is the subtop of the areas. The most evident rock in surface is an intrusive of diorite granite composition, and there are some breccias, and these breccias are mineralized with copper and molybdenum. So, what's the problem that we want to solve with this survey? So, basically, is detect the breccias with copper and moly. So, this is the configuration of the current dipole. This is the lines in the survey area, and this is the current dipole. This dipole is 6 kilometers away from the lines, and have 2 kilometers of length. And we are using this scalar array. We are measuring 5 electric fields and 1 magnetic field. This is a perpendicular magnetic field. This is the most simple array in CCM. Okay. So this image shows where the mineralization of moly is, and this mineralization is related with the breccias. Okay, the separation between lines is 15 meters, and the length of this lines is 1.2 kilometers. I am going to show the models of the resistivity models of the central lines that are covering the breccias. So this is a surface that is involving the zone where moly is greater than 250 parts per million. Yeah, and we are viewing to the north. This is the place where the breccias are outcropping. So you can see we're using an invert color table. Yeah, this is for high resistivities, and this is for low resistivities. So we can see then that the electrical resistivity associated with breccias is a low resistivity, and the resistivity associated with the intrusive is a high resistivity. So this is the model for this line. This is the central line. along this way. And this is the surface that is involving the zones or the place where copper is greater than 5,000 parts per million. So you can see then the relationship between these zones with geochemical anomalies are related with low resistivities or high conductivities. So sometimes we want to validate our models using additional information like the data of physical properties, in this case resistivity. There are some drills in this area, and some data are collected from the cores of the drill. So, yeah. So we have then we have the information of how is resistivity along one drill. So then we expect that our model obtained from surface data conciliates with the data taken in the drill core. Entonces, then this is the zone when resistivity is lower than 50 ohm meter. So there are many drills in this area. So we are seeing the results of the data in the core drills. Yeah, the line where it's narrow is associated with low resistive, and where is wider is a high resistivity. So we are, this is a plan view, and we are seeing this line. And this line should be in this place. And we can see the continuity of the low resistivity from the line to the north to this line. Yeah. And this line is in this place, and continuity exists in this line too. So because our practical problem that we want to solve is first obtain the response of this ratio, and then when we know that response, that resistivity response, we want to explore in a most bigger area. So we are looking the results in this place, and we collect data in these areas, in this one and this one. So but we have information from another geophysical methods. One of them is residual Bouguer anomaly, yeah. And we can see that in the zone where the ratio that where the drills are is associated with a low anomaly. So another information that we have is magnetic. This is a map of a residual of reduced to pore, yeah? And we can see that the zone where the pressures are related with low resistivities too. Yeah? So for solving our problem, we have information from three geophysical methods. We have resistivity, we have density, and we have susceptibility. So the criteria for choice these areas that is that we are looking for areas where there are low susceptibility, low density, and low resistivity too. Yeah, this is the map from 2D resistivity models obtained from lines collected in these areas. So then the program, the drill program is focused to explore these areas, these red areas. Some conclusions about this survey is the low cost and fast collect of CS AMT data. We collect 60 and 67 kilometers in 2 months, and we have good lateral resolution because we use dipoles of 25 meters, and the depth of exploration is about 350 and 400. And where the core drill data, we can establish the area to interpret the data. So to locate these breccias with copper and molybdenum, we should explore in areas with low resistivity, low magnetics, and low gravity. And as we see 2D models of resistivity. Okay, 2D model resistivity have good fitness and are conciliatory with the petrophysical data. And the areas of interest should be shown with additional information like geochemical surveys and drilling. So I'm sure that some work should be done for a better results. Probably 3D inversion of magnetics and gravity data, for we can relate the results with the resistivity model and inversion with that results of 3D inversions.
Any questions?
On your test example that you're going to use as kind of a template and a learning module, did you try putting the control source on the other side and then running lines perpendicular, just to see what you could see? Because your body is closed, so it's kind of three-dimensional, and to at least see what two polarizations would provide.
Okay. For this survey, the current dipole was to the south of the area, but we did this is not a detailed survey. This is only for recognition. So, but this is our interest now because we are working basically with this array. So our intention is use a vector or tensor array, but we have no experience with measure data with two dipole currents. So. Okay.
It's the terawatt.
So here's the mic. So we can clip this. Research about the Republic. And then you've got laser pointer. And then to flip your slides, just
Hi everyone. I want to talk about this new line of business from GeoTem in engineering. Like 1 year ago, we started with a new idea to make our platform software, geophysical software, for at the moment no commercial use, but internal use because GeoTem have like 13 years in experience. And the majority of these years is from making TDM soundings in all the national territory in Mexico, with a data bank like 20,000 soundings, TDMs, for different clients, for different applications, hydrology, geothermal. At the days we start to incorporating our service in the offshore exploration, and a lot of people make a big effort to this new line of processing and interpreting our geophysical data. At the moment, the name of this platform is TerraWare. It's a integrated platform with a lot of modules. We include the first module is called TerraWare Potential. This includes potential methodologies, gravity and magnetics for inversion, 2D and 3D inversion. This model can make all the processing, all the line of process to the data, and the final inclusion at the inversion. We use 2D inversion, some like called density tomography for first model approximation, and this model can invert with metaheuristical methods like simulate annealing for gravity and magnetic. But this is other topic. In this talk, I talk about the TerraWare TDM software. This is a model for transient electromagnetic in time domain for this sounding. In the department, in the development department software of GeoTem, we are 3 people. I'm geophysicist, and the other people geophysicists, but they are specialized in the scientific computing and physical and mathematical basis, something like that. After me, Francisco here talk about the structure of the program and other related topics about the architecture of the interface and the coding developed for this platform. Here you can see the process diagram for the TerraWare TDM software. You can start with all the related with the processing. After that, modeling and inversion. The first issue is you can you can take your referencing data at the moment, at the present, and the prices moment. You can put in your field data in all kind of type of data, including USV for universal TEM data, or .TAM for TIM-FAST for different systems for the TDM soundings. And you can make all the line of processing to obtain a resistive curve this curve is gonna be the first stage to make a modeling of this apparent resistivity, sorry. And you can make a direct modeling, electromagnetic modeling. For this stage, we use open source. Dieter helped a lot in this issue because the open source, all the lists that he shows before, it's like a CSIRO. It's like a program for open source access to inversion modeling for electromagnetic data. And for this stage, for modeling and inversion, we use Beowulf. It's an algorithm for Gauss-Newton Marquardt, and Occam, the smoothest algorithm known by everyone. Beowulf is from CSIRO project, the AMIRA project for electromagnetic modeling, and the Occam algorithm is from Scripps of San Diego, the Consortium of Electromagnetic Methods. This algorithm is open source, and we make a modification to include in this platform. The new of this platform is a modern interface and some more robust, and you can make easy you can make in an easy way all your referencing data, select soundings, make profiles. At the moment, we only include 1D inversion to make your electrical section. This is one of the other part of the program. You can see the electrical profiling, the interpolation. We include a lot of methods of interpolation by the electrical section. And finally, you can edit the information. And this is the reference for the open source codes for the inversion approach. And this is one of the term that we want to show to make that if you have a general idea to how works the software. This is one of the hydrological projects that GeoTem have in Zacatecas for mining project, and this is profiles, and we select this one in yellow, profile G. Area we make a TDM acquisition and CSMT for hydrologic prospects. This is the first stage of the program. You can visualize the data. If you only include the points, this is the 6 TDMs that we enter in the platform, and you can see all in ArcGIS libraries. Is ArcGIS open source libraries. You can see immediately your referencing data, the 6 points of TDM soundings make in Zacatecas, and this is the general interface of the TerraWare TDM platform. Here, all the interface is developed in Qt, and all the architecture of the program is C++. And the other guy in charge of all the coding and the background is scientific computing. He doesn't here, but Francisco can talk about the numerical and all the background mathematical analysis to include this kind of examples or operation to processing, to modeling, and invert the TDM data. The section of the interface of TerraWare is you can a database. You can see all the soundings in form of the list, and you can visualize the chain process. If you can see, it's preprocessing, processing, modeling, and inversion. And these other models, you can see the map that I showed before, and the geoelectrical section, or this processing window, and all the parameters of the sounding. And you can it's like any sounding TDM. You can charge all the how do you say corridas? The runs of the sounding, and you can visualize it, obtain an average curve, to make a new apparent resistivity curve, and this is the parameters of the acquisition, the number of channels, time window, the gain, and I can't see. Another related with the area and the name of the contractor and this kind of topics. This is one of the next step for preprocessing. You make all the runs in the field. You make sure that the points that you measure in the time domain for late times, it's very accurate, and you can combine these runs to make a new curve, like a juice curve. And in this step, you can eliminate for runs, corrected for gain, cut for the curve for the early times, and the cut for the curve for the late times. And you can make a correction, eliminating some points that is also just out of the values that we make in the decay curve. And this other interfacing for processing, you can the new apparent resistivity curve, and you can make other kind of analysis like sensitivity analysis. You can obtain the complete curve for resistivity for late times and early times. This is one the modeling electromagnetic for TeraWare TDM. This is using for the open source code for Beowulf, and this is the initial model, layer modeling, and you can put in parameters with the number of layers, the width of the layers. This is the initial model, resistivity versus depth, and you can put in the limits of depth and the limits of the resistivity. Well, I think at the moment Paco can talk about all the background analysis that he made to include this related topic that I mentioned before.
Okay. Some details about Alfredo said before. This is not an average curve. It's not, but is an adjusted curve. That is because an average curve involves modifier data. So this is not a modifier data. From every runs of the sounding, we calculate the average and the points, nearly points of this average curve is what we took for the adjusted curve. First of all, we are finishing the software yet. We are working, actually, today we are working yet, no? So there could be some errors or bugs in the software, as everybody could know. But we are working to perfection in the process. So this is the apparent resistivity to asymptotic to late times. We can make we can calculate the formula when the resistivity, the complete resistivity for early times and late times. In this case, these both curves are not crossing, but in another cases they should be crossed. And we have to take for the complete resistivity the green curve for the early times and the red curve for the late times. This is depending, both curves depending on the harmonics we can take for early times and for late times. So this is the modeling interface. So we can see here the layer models, and we can choose an initial model from resistivity versus depth, which is coming from the curve of complete resistivity from a calculus. So we can choose this curve, or we can choose an homogeneous semi-space, and we can choose the logarithmic scale or linear scale. So these are the equations, the analytic scheme for modeling. This is the integral for air, the integral for the I layer, and the N layer, and this is the magnetic field. We can see here the Hankel transformations, and some coefficients. So here is the inversion process. No, we have two inversion process: the Beowulf and the Occam. Occam is the smoothing inversion, and Beowulf is a Gauss-Newton-Marquardt inversion. Here is the parameters for each one, and here is the equation system for solving for the Occam, the partial derivatives matrices, and the Jacobian. So here is an example of the Occam inversion of this curve. Here are the parameters, the initial error, the final error, the number of parameters, etc. Here is the layer model, and in blue we have the inverted model, the smoothed inverted model. Here is the Beowulf, Gauss-Newton-Marquardt, and the parameters of convergence. And here is the curve in blue of the inverted model. There is a better adjust in the curves, and at the same as before. Here are the parameters: final error, initial error. So we can see some benefit of this inversion is that we can invert also resistivity and depth and thickness. In Occam, only we can just invert the resistivity. This is an example from a commercial software versus our software, TerraWare, and we can see here the inverted model from this sounding. And here is the other step from the software. In the section of map, we have the soundings, and we can select one line section, and we can select the soundings which we want to project into the line section. It's easy. It's an easy way. So we have our section, and we can choose the interpolation could be linear, kriging, other interpolation. We see that in this type of data, of TDM data, is better a bilinear interpolation. We can choose the scale x, the x scale and depth, and to save the project. And here is the section of this example of our soundings. We have yet some problems with the color theory. It's not so easy, so it's not so pretty, the section. But we, as mentioned before, we are working yet in this software. Why? Because we have to, before to commercialize and all other things, we have to perfection this software. And this is the section of the commercial software, and we have a comparative between both softwares, and an interpretation from our interpreter Arturo. We can see the faults, the discontinuities, possible discontinuities, and the resistivity layers. Okay. Thank you.
It's very recommended to include the error bars in the resistivity codes. I think this is very important for us.
Okay. Thank you. In the resistivity curves or in the
codes, in the resistivity codes. The first things that we analyze
for the
is
runs?
the error bars. Yes.
Oh.
We have to know what is the quantity of the
yes. In fact, indeed, we have to make it, but there is problems in the graphic,
yes.
At the time for programming to collocate the error bars. Yes.
Any other questions? Thanks.
Sure.
Yep. You've got on your, we'll do it up here.
Yeah.
What's your name?
And
While Lindsay's setting up, I just want to make a comment. I've been really impressed with the talks. The one talk that we haven't heard anything about that I was expecting to hear a lot are water issues in Mexico, especially with the subsidence.
Yeah.
And I don't know, nobody's.
Yeah, the talk is extremely necessary. I know I very know the case study, but we can talk with Carlos Pita, and he make the talk. If you want, this talk existing.
Oh, that would be good. I think that's very important to come back with some knowledge about just generally what's happening with water, the substance, just some understanding about water issues.
We have some excellent history about subsidence.
We don't have, but we would like to, because it's, from what we read, it's a very big problem in Mexico City and perhaps elsewhere too.
I
I can email you. Sure, that would be great. I connected to the internet. Okay. I can email Doug at GeoSci.xyz. Yeah, sure. Just email him.
For me?
Trouble connecting. Yeah.
So just to clarify, so was there anybody else then who would like to talk yet this afternoon? Pardon me?
Okay. Oh, here we go.
You can see it on TV.
Now it's connected. We're dropping slides today. Interesting. It's still saying. Sorry. Okay, let's also just send it forward it to
Pose your problems or explanation that you helps. I think it's a little shy, but if you open and you just invite him to pose their problems,
Okay.
doubts, or something.
So while we're trying to get the next talk up, might be an opportunity if somebody has a question about anything, you can tell us what your question is, and we could discuss among the group, or some of us might know something about how to answer that. So it's a good time. We're waiting for email to open up here. So anybody has a question? Yes.
I would like to use the opportunity to. I would like to use the opportunity to make you a question about the early time behavior of the transient electromagnetic curve, which I have never understood. I really like your way to explain the phenomenon, and maybe you can give a nice explanation why the early time curve is doesn't arrive with time, why is it constant?
So the early,
Yeah, in transient electromagnetics, you have a homogeneous half space, and you make a sounding, then your maybe I have to think about it another time.
that sounds like a question that we should put on for EM GeoSci.
Let me think
Yeah.
about it.
Well, actually, that's a. Yeah, without answering that question, that's exactly the kind of thing that is really informative. So you have a loop system. So here, I think it's an interesting question that has been raised, but we need to think both about the question and the answer. But sometimes these are the things that are really informative. So suppose you have a loop system, and then you look at a very early time, and you find that its behavior is a bit different than what you might expect. So at some point, things are going to kind of decay with a particular rate, but if you're in very near field very early, things might change over and asymptote. And I think that's the question, and the way to make really good use of this is to first of all have a numerical example that shows it, and then to start trying to promote the question of why is that, and then ultimately that has to go back to the formulas. So you could look at, for instance, a dipole in a whole space or over half space, and you find that there's actually many terms. If you look in the book by weight, then there's a lot of terms in there, and at some point this term is useful, at some point that term is useful, and you can use those asymptotics to kind of understand what the nature of that curve is. And by doing that, by linking the mathematics with the numerics, with the visual calculation, those things turn out to be really powerful understanding devices. So I think that's good. You should verbalize that and send it to us. Did we get that going?
Yeah. And just so before she gets going, is there anybody else who wanted to present?
I can do some short presentation of sequences.
Okay. Do you have it on the Perfect.
Should I pass it to you now?
Sure.
Well, I'm going to do a fast presentation about my poster that I present in the UGM. So this is my work from, I'm a student, I'm a PhD student. My name is Ana Fragoso, and I'm doing my PhD in Sejeo, in Curiquilla. Well, I'm working over the Paleopetrozoic province in the southwest of Laurencia. That is apart from Sonora and Arizona. So, before I was working with, before they have been doing some geologic work in the area that limited these three principal provinces in this region, that is Mojave, Yavapai, and Atizapán. The geologic work, the limit of the geologic work is the black line over here. I don't know if you can make it so. There it is. Okay. The black line is a previous geologic work, and last year I have worked with gravimetric and magnetic satellite data. I process it. I compute the field, and also I make a 3D version with a program called 3D inversion from MATLAB that was done by Gomez Ortiz. He used the older world formula for the inversion. So with the field and the 3D inversion map, I suggest a new limit about the province, that is the magenta lines over here. And next, we are going to do 4 empty profiles. And in this work, I presented the first one, that is this one over here, that is from Puerto Peñasco, Sonora to Ajo, Arizona. Well. I can use this. Okay, just move to the right. Thank you. So for this work, we use the NTU 2000 from Phoenix. And here I showing a picture of the selection of one sounding. Here's a central station, one electrode, and I don't know if you can see the how do you say bobina in English? Okay, and the vertical one over here. So to process that data, I calculate with while bar the strike, the electric strike, and I have two principal orientations. One for less 45 and the other one from 45. So we take this one because in the region we have a principal structure. The basic operation is the same orientation that we have here, and also this one has the same orientation of our profile. Also, we calculate the curve to the inversion, and also the tau. The tau that I used was 4, and the inversion number were 75. So this is my result of the empty profile. We have it doesn't look well, very little error from 2 to that 8. Here I'm going to show you the interpretation. Okay, for publication here I put a satellite image for Google Earth. We can see that we have a lot of sand, so we don't have a lot of outcomes in the region. So I put the geology map here, and here with different colors I put the 3 different provinces, the Paleoproterozoic province that we are working. And here I put the geophysics limit I have proposed, and here I'm marking, putting the geological. Well, here the more resistive we are related with the province, Mojave, Yavapai, and Mensasal. And also we are seeing other things like this one, that this is more conductive, I forgot. Cuerpos, ¿cómo se dice? Cuerpos. The more conductive curve. This one we are related to the astronosphere fluid that help to the pinnacle, ayudaron a que el pinnacle se formara. That fluids that help to the pinnacle to lava to rise, yeah. And also here we have the porphyry from the mine from Ajo, Arizona, and down we are seeing some conductive body that we are related to maybe the fluids that also help to that porphyry occurs. We are also proposing to some slab from firearms that maybe are here for these two resistive body for the subduction that was over there in the Miocene. And also in here the red stars. This is my result from the 3D version that I made before, and also we are seeing a good correlation with the Mojo profundity in this region. So we are working with this. So this is a first profile.
Okay, good. Any question? Yeah, Oscar?
Yeah. How long time did you
At the stations, about 16 hours per station.
I have one question. That Farallon plate, is that the one that's, is that still subducting? Is that the one that's still causing earthquakes?
No. In this version, it had deposited that it stopped about 12 years ago, 12 million years ago.
Okay, then I think we have one more talk. Yep. Thank you. Oh, another question here.
Yeah, there are crystal thickness estimates using station receiver function.
Yeah, there is in the image. There are there are a lot of work in the area about that, but they use almost the same station. From Puerto Peñasco, they have the more recent study is from Fernandez y Campos. That is that. This one, and it is from the yellow triangle. I don't know if you can see it here. It's about 20 kilometers, and also Bashir in 2011 present some work in Arizona. That this is the example for two stations from my profile. That is about 30 kilometers. Okay. Thank you.
I had on my list to talk about ZTEM, and I had a case history for Balboa, but we're going to hear a local case history about ZTEM. How many people have heard of ZTEM? I think I asked that question. Wait for a minute.
Okay. Hello, my name is Rafael, and I'm going to talk to you about the ZTEM. This is a whole presentation. Didn't see for a while, but I found it, and it will be interesting that you know about the system. Basically, the system, the idea of the system was developed by Worth in '59. Some results at the Athabascan sediment area in 2008. We will talk about that later. So we are going to talk about the introduction of the method development, how the system was created, the actual system, and we will be some little bit very light modeling, survey results, and conclusions. Well, as I mentioned to you, Dr. Worth present the AFMAC technique that it consists in measuring just the magnetic field for the MT instead of magnetic and electric. The idea came, as we already saw yesterday, that in fact it's very difficult, if not impossible, to measure the electric field in the air. So it's not possible. We need to deal just with the magnetic field. So in the 60s, early 60s, McFarland was they developed some system for working on the ground, and they didn't have too much success applying the technique because of the electronics of that time, and also at the same time there were developed some other controlled source techniques, so it was forgotten this technique. So in AFMAG, what we use is the natural source, as we saw yesterday, the sun flares, the magnetic field of the Earth, their interaction, and also the lightnings. So when we have all of that, we have a lot of energy around the Earth, and we use that. One limitation of this method is if we have some thunderstorm very close to here, nearby, we cannot do anything because it's too close. And the source, it's not going to be proper for the technique. Anyways, the way that what we do, it's working with frequencies in the audio range. And by now we can work from 7 to 720. Because when we, at the time of this presentation, we were in 30 hertz, as lower, and the higher it was 360. But we improved the electronics, and now sometimes we are able to work up to 7, down, and 720 at the top. That's another interesting thing for MT. When we have bases on the Earth, we can leave it there for so many hours, as we already saw in previous presentations. So, but in here we are flying about 80 kilometers an hour. So we have soundings every 0.4 seconds. So it's very little averaging. We have lots of noise and restricted range of frequencies. So it's all of that. It's a limitation for the system. But if you think in all of those limitations, and that we are able to go 2 kilometers in depth, so it's very convenient. We already saw that the source, the natural and the ionosphere, as we saw yesterday, they are conductive, so the energy bounces back and forth from the ground to the ionosphere. And at daytime, that energy is lower than at night time, but in airborne systems, we cannot fly at night, so we just can do on daytime. So that makes that in northern regions or southern regions, we cannot fly in winter time because there are no storms. But in going further to equatorial zones, we can do the survey all year long. There is no problem. Also, there are some other particular areas like Papua New Guinea, that they have lots of thunderstorms in the coastline, and the island is not so big, so it's difficult to fly there. And they have areas of the island with 50 hertz power, and some others with 60. So it's very difficult to choose which filter to use for that on that area, but it happens, you know. And when we are flying the survey, we have a signal from all over the world, from all over different sources, and it creates unknown coupling. But we can assume that the source is y azimuthal direction, and we just deal with the magnetic field as primary. So we can see in this imaging that this skin depth, how it is affected by the resistivity of the top layer. So while more resistive the top layer, we can go deeper. In general, the theory is that we have a relation between the vertical component with the two horizontal components, and those ones are related by this vector, the t vector that is known as steeper. So that's why the name of the system, because it's the component vertical and it's the deeper vector. So when we have the airborne system, the behavior is if we assume we are thinking about some thin layer as a conductive model, and the model is perpendicular to the flight direction. We will assume that it's very long, striking both directions, so it's some sort of quasi to the model. There are two basic responses: the electric and magnetic response. We are assuming that we are flying on the x direction as always, and the conductor is in the y direction. So we're flying over x, and the thin layer is on y. So with that, the electric field response follows the slide. And it has some induction. And the magnetic, they are on the HX field parallel to the strikes, and then the phase of exit, it's very small for this model, and the challenge phase is happening at a small moment due to the thickness of the model. But this is very important because we have the relations xz and xy. It's what we are going to deal with the problem that we have. We have here some response of the in phase and quadrature response. For this system, we read both in phase and quadrature. In line, it's the relationship between the magnetic vertical and the horizontal in x direction. So for the model that we saw, the plate, we have this response. For different frequencies. And now, if we are flying lines in some grid pattern, we will see what's the difference between the profiles. We can see for potato-shaped body, how it goes the profile when we cross over it, and how it changes when we are close to it but not over. So that's the basic idea for modeling. Now, for the development of the system. In early 2000, the company came with the idea to make it work. Because in the past we were trying, but it was unsuccessful completely. So in 2000, we started with those small loops that they were too small. So after that attempt, the Canadian government provided some funds, and it was developed new bases, new loops for the bases and for the airborne system. Also, those ones end on the same, I mean, very small loops, and they were not effective to measure 10. But we were in the right direction. So the next step was making very big loop, flying loop, 7.4 meters. And at that time, engineering decided to do with the same frame the loops for the base. As we saw for the ground empty, we need some base and we need some moving station. In this case, it's the same. We have the base that we try to keep within 40 kilometers of the survey area to assume that the field is the same for the base and all the areas that we are flying. Also for actual systems, we have 2, 3, or even 4 bases. So if the block is too big, we can change or use more than one base for processing. For the airborne loop, we have 3 GPSs, 1, 2, and 3. With those 3 GPSs, we can control all the time the attitude of the system, because what we are measuring is the vertical component, and this is because of the method, the AFMAC method. In that one, there is no response if all the if the half space is homogeneous. So we don't have any response, but it's not going to happen in the Earth. In the Earth, we have all kind of discontinuities, and then it's what we measure. So the horizontal field should be 0, and the vertical is the one that we need. So that's why we have the 2 bases, the base with the two coils, and we can measure the magnetic field horizontally, and get the relations x to c to x, and c to y. So those bases, they were too big and very difficult to deal with them in the field. So the next step was to reduce the size of the base to 3.5 meters. And again, we were working with 2 bases. With two coils to measure the X and Y field. This one was working for a while, and also from the previous imaging, we can see that why we started with 3 systems, because it was 1, 2, and 3. We already have the 3 airborne loops. So then we will develop those new bases. This one is the second generation of bases that were used for production and for selling surveys. And this is the loop flying, the airborne loop. It's towed by 90 meters tow cable. It's very long, so we need experienced pilots to fly it. It's very long, the tow cable, but it's possible to control by the pilots. It's that long because we need to keep the machine out of the as far as possible of the loop to reduce the noise. So in general, the cable, it's 90 meters long, and the loop is flying most of the time something between 50 to 80 meters above the ground. By now, we reduced the speed of the helicopter to 80, 90 kilometers per hour. We still having about every point, we are still having 0.4 seconds every sounding. This stays more or less the same. And we measure from, as I mentioned before, from 7 to 720 now. There are more, but in general, the most reliable are from 360 to 30 for regions with 60 hertz power. And it's due to the filtering that we need to use. Here is a sample of packets recorded on the X and Y coils and the vertical. This is the airborne, and those ones are from the base. We can get some polarization ellipse, and we have the power spectrum. And we can see that we have lots of energy here, and then it goes almost to zero, and keeps in the same way for higher frequencies. So that's a problem. We can go up to 720, but it's very hard to get it at daytime. Properly. No, so what we do, it's we grid the angles that we measure with the what we measure it for, because we were looking for some way to show where it's the anomaly, and the anomaly always is when it goes. As you remember, when we saw the thin plate, the change. There is a change exactly over the anomaly. So to change that, we rotate the phase to have the anomaly just at the center. That's why we have those two panels. Same thing, but in here it's the anomaly, and in here. So it's easier to see with the phase rotated instead of in phase. Yes. That. So the main idea was to combine the components in single presentation. That's it. We have we measure Z, and we have the relation with X, that it's the line direction, and Y, that it's perpendicular. With those two, we have control of the ground. Of the ground conductivity, the distribution that we are measuring. But we were looking for some way to present both in just one map. So with that idea came the total divergence. That is the relationship, the Zx, Zy, that they are added. So it is minimum over some conductive. So we have to invert the color bar. Otherwise, we will see nothing. So this is a comparison between some P10 results at 1900 milliseconds, and no, microseconds. And this is with 49 hertz, see them in phase with the total inverted. So we see the anomaly exactly at the same spot for the same area. There are, as you know, there are many examples of comparisons of C10 and P10 data from all over the world. So anyways, this comparison of MAC, total magnetic intensity, and total divergence. And we see again. And that one is just total magnetic, it's not corrected or anything else. So for the Alaskan, it's interesting there because we have a very thick layer of sandstone. At the top, there is the alteration zone, that it's over some granite, and in here we have the uranium. So it's some interesting because of the depth of the sandstone that it's overburdening the inconformity. So these ones are the models for the area, and we can see the alteration associated. And this is the model for forward 2D. So we have some some intrusive body in this basement, and we have the sandstone at the top, and quite simple model. So with that model, without the alteration, we have here some alteration. Without the alteration, we have these models. What you were saying yesterday, what we are going to get if we have some model. So it's always like you are thinking what I'm going to get. So it's not too much response. But at the moment that we have the alteration at the top, the response is bigger. And now we can see what we got on the field. On the field, we have the change of phase here. We have it here. The crossover, it's here. Very strong crossover response. And this is when we go with the again, we have very strong crossovers here. And now we see at different frequencies how it goes deeper and deeper, and how it's the anomaly zone going all the way deeper. This is the inversion from the data got on Zoom. In conclusion, yeah. This is just for Canada, but worldwide, closer to the Ecuador, we have full year. In Canada, we have 3 seasons for flying C10. So by now, it's basically the end of the season for flying in north or very far south. By now, we already went to 7 and 720, depending on the strength of the signal. For the signal-to-noise ratio, it's very good with the fixed horizontal base and the flying error loop. By now, we have different bases. I think I have another picture. Let me check. No. Well, after that station that I showed you, the 2.5 meters, we went to 3 coils for 3 components for the base station. That one was 2 meters on each side. They were square, and we were trying to fly with that, but it was proved that impractical due to the fact that it's very noisy. It's very difficult to fly 3 coils of 2 meters with keeping the noise levels low. So we decided to be back to the just 1 coil, the vertical coil, and for the stations now we have some coils of 3 meters in length. They have a iron core, and they need to be calibrated because it doesn't matter how well we try to do it. There are small differences on those coils. So we calibrate the base and we calibrate the flying loop. That's not that much problem because it's the core, it's air, so there is no problem, not big problem on that. But the other ones, the bases, that they are very convenient now, and that's why we use several stations by now, because it's very easy to install those. It's 2 meters and a half pipe. That's it. Maybe a little bit heavy, but it's very easy. Anyways, by now the system is successfully flying all over the world, and we are getting very nice results, especially if you think that we can produce the data with very small difference in cost, just flying magnetics. So it's very convenient. In the other hand, there are some several jobs that we combine the CTEM with MT, ground MT, like the example that we saw previously. If we fly all that line, that it's very easy. It's just one flight. It's 180 kilometers. We can have very nice, very detailed section all over it, and because it's almost nothing for 180 kilometers. So, anyways, if you have any doubts, please let me know. Questions? Thank you.
Are there any questions?
In your expertise, which signal is more sensitive to the positive bodies, the total divergence or total mass rotation?
Well, for conductive bodies, I think it's more, the question is more related to which method should I use for the surveying. But because the total divergence, it's just a way to present the data, to make it easier to locate the anomalies. Thank you.
Yeah. I have a question. Are you running a project, random perspective project?
Yes, we were flying. We had to fly lots of survey jobs with CTEM and BTEM here in Mexico. The last one was in Guerrero, like early last year.
So for uranium?
Yeah, no, it's for gold, and we have some other jobs this year in Sonora. With CTEM. With the BTEM, we have further more jobs here in Mexico.
Any other questions? Okay, then I think what we'll do is take a 10-minute break.
Very short.
And then what I'll do is show you some of the open source resources that we've been developing, and also how to access the apps and how to get plugged into the SUPEG community if you are interested in getting up and running with some of the open source software that has been developed. So with that, we'll grab a copy.
Thanks very much.
Thank you.
Yeah, it seems like in this area, where there's so much interest in geothermal,
Yeah.
the combination of ZTEM and MT sounds very reasonable.
Yes. Yes. Actually, for this one, it was some combination of that one. And There's some other slide, but it's not a light show. But I didn't bring it, but it makes the comparison with some hundred and something MT soundings with the CPM data. So it's interesting.
Yeah, we did some work years ago on, I forgot where the name of the place was, but it was just a combination of the MT and the Z10. Just using that Z10 to get that upper surface structure, and you don't need so many MT stations. You just want to look deep, you want to be able to calibrate that conductivity. You need something to calibrate conductivity anyway.
Actually, I forgot to mention that. It's the problem is just measuring the magnetic field.
Yeah.
We need to know the conductivity. So there is a way around to do it, but the best is to have some real values.
Well, if you have topography, for sure.
Yeah.
But if you have topography, then that can help calibrate things.
Yeah.
What, the audience is sleepy? No, the audience is awake.
Are you good with the mic check?
Sure.
So if you just like
Yeah.
push the so it goes green.
I can just start. I gave you a shout out there. What coming. Okay, we're going to start. Some people are still out having extended coffee, but we actually have to be gone here shortly after 5. So we really only have about an hour. So Lindsay's going to take you on a walk through SimPeg, show you the site, talk a little bit about the software and how to access the apps. And yeah, that's going to open up a portal to you. So we won't be able to talk about everything, but at least you'll have a vision for what is there, and then you can use that and communicate, and we can get conversations going. So that, Lindsay?
Perfect, thanks. Thanks for everyone for sticking with us. I know this is a long couple of days. So we'll start. I showed you GeoSci earlier today, but that's where we're going to start again. So this is really the portal site to a lot of the resources that we've been working on at UBC, and hopefully actually branching out beyond UBC to other contributors and other people who find this material useful. So there's a few different things, and one of them that I want to point out here is this is called the GPG. So this is basically a web-based textbook that has been created for introductory applied geophysics. So we've been using this at UBC for an undergraduate geophysics course. It's mostly geologists and geologic engineers who take this course. So it's really a once-over lightly of all of the geophysical methods. We introduce everything, gravity, magnetics, seismic, GPR, DC. So this is meant to be a useful resource for an introduction to geophysics. It is open source, and it's meant to be something that you can add to, you can edit things and all of that. So if there's examples, if you're teaching a course and there's an example that you have that you really like and would like to have it included, we can work with you to make sure that that happens. There's already a professor in California who started adopting this as his prime textbook, and we've been working with him to get some of his material and some of the things that he needs in here. The next one to show you is EM. And so this is really the textbook that's been developed for this course. So what we've done here is there's a few different sections. So you can go through, there's things like physical properties. We go through all the fundamentals. Geophysical surveys, so we'll walk through like DC resistivity, what is the setup, what's the basic physics, all of that. The thing that I really want to point out here is the case histories. So these are all write-ups that accompany some of the case histories that Doug showed yesterday. They're all broken down into that same 7-step framework, so they've all got a fairly similar look and feel. And for the most part, they're based on a published paper. So this is the high-level overview, broken down into those 7 steps, and then we reference the original paper if you want to go back and see all the details. And in particular, if you have a case history that you would like to contribute as well, that's something that we can work with you to get that in. It's exciting to see this grow and see applications in different areas. They're meant to be like high-impact stories. We want these to be things that it's a fairly clear story and something that you can walk people through as an introduction to electromagnetics. The next thing I want to show you is the apps. So if you come here, you'll see that there are 2 different styles of apps. So we have the EM apps, and these are really meant to be like GUI style interactions with Maxwell's equations. So you don't really see any code. All you're going to do is run a Jupyter Notebook, and I'll show you this in a minute. And then you'll get some widgets and some figures, and that's it. The other style, and I'll show you these as well, these are the simulation notebooks. And so what these are is these are examples that will actually show you how to use open source software like SimPay to actually run an EM forward simulation or an inversion. And it shows you all of the code. So if you want to see all the details of how to actually code up and run a forward simulation, this is where to go. So let's take a look first at the EM apps. There's a few different ways you can access them. If you're comfortable with GitHub, installing your own Python environment, all of that, you can just download them directly from GitHub. The thing that I would recommend for most people is that you start by looking at Microsoft Azure. And so let's go here. So what this is this is actually a cloud service that Microsoft offers for free for small notebooks, where we can actually just get this running on the web. So here, this is what you'll see when you click on that link at first. And you'll notice that the run button is grayed out. So right now, we're not actually logged in. So we just need to sign in. And so if you don't have an account, it's free to sign up. So there's no cost associated with that. And then right now, this is a library that's hosted. Yeah.
Is this the normal standard Microsoft account? Or?
Yes. Yeah. Yes. So right now, the run button is still grayed out, although I'm logged in. That's because we need to actually make our own copy of this library. So it's kind of nice. It grabs and keeps your own copy. So if you want to make notes or change things, it'll persist and it'll stay with your account. So we'll make a copy here. And because Doug's already made a copy, it's asking, do we want to replace that? And we can update it. So we'll just replace it. And then now we can actually see that the run is live, so we're good to go. So you'll see there's 3 pages of notebooks. And so what we've tried to do is name them by the method first. So we've got a whole bunch with DC. Some of them are 2D, some of them are 2.5D. So that means that we simulate a 3D source, but the model is 2D. There's examples for frequency domain EM, and there's also examples for time domain EM. And so let's grab the DC layer cylinder. So what this is doing, when I clicked on this, we've spun up the server somewhere, courtesy of Microsoft. And so they're launching a Jupyter notebook. If you're not familiar with Jupyter, it's an interactive computing environment. It's really been used a lot in the Python community, but it doesn't care what language you use. It can interoperate with a lot of different programming languages. So I'm just gonna make this bigger so you guys can see. There's 2 ways you can run the Jupyter notebook. So each of these cells is like a code cell. So you can do Shift-Enter to run them one at a time. The other thing you can do for these apps, if you just go to Cell Run All, it'll just run them all in order. And that's fine for the apps because there's like three cells of code. So what's happening here is we're installing a package that's built. So this EM examples package really just builds plots, basically. And the simulation engine is SimPeg. So it's just going to go ahead and install all of this. If you set this up on your own computer, you would only need to install things once, and then you have them. Then we're going to import some standard Python packages, as well as our EM apps. And then we've got a short little write-up and a couple questions. So we show you what the setup looks like, what each of the parameters are. And then here now we have our app where we can go and play with the cylinder and the sphere and have a look. So in this case, we have a resist layer. So to Dieter's question earlier today, the comment that came up is that we were looking at currents versus electric fields. Let's forget about the cylinder for now, but we've got this resistive layer. We can see what the currents are doing. So in this case, they're bunching up mostly in this top layer. And then if we flip to our electric fields, you can see what changes. And so here you can go ahead and look at charges and all of those sorts of things as well. Are there any questions with that? Okay. So the next thing that I'll show you is the simulation notebooks. And I'll also show you a bit to do with SimPeg. So if we go back to GeoSci, the apps page, we can again go to these simulation notebooks. And so this is we've again got like a separate GitHub repository, so if you want that, you can grab it. Or we also have it up on Azure. So this has a few less notebooks because they really are, we're trying to break down all the bits of code, what's going on, so it takes a little longer to write them. So in here, we've got a DC example. We have a couple of frequency domain examples. And so if you remember yesterday seeing the example of the currents in a sphere, these will run that for you, so you can actually go and reproduce some of the figures that you saw yesterday. And then the other thing that I'll walk through in a moment is this MT tutorial. So recently we wrote a short leading edge article that basically builds up the forward simulation for a 1D magnetotelluric problem. And then we go in and investigate and show some of the important choices that you make in the inversion. And so this serves a couple purposes. It shows what those important choices are. So looking at things like the Tikhonov curve, your stopping criteria, your choice of beta, your choice of parameters in your regularization, so how small or how smooth you want to look. The other thing that this does, if you look into a few more of the details, is it'll actually show you how to build up your own forward simulation and hook that up to SimPeg. which has a lot of machinery for the inversion. So before we jump into that, I want to just show you a couple resources with SimPeg and give you a bit of a picture of what that is. So I'll go here. So this is the SimPeg site. So again, you can access it from GeoSci. And so SimPeg stands for Simulation and Parameter Estimation in Geophysics. And so what our goal here is to actually bring all of the geophysical methods into one place so that you can have a consistent way to access them, play around with inversions. And one of our big goals has really been to give you hooks and the ability to play with all of the pieces. So that if you want to go in and look at the fields and fluxes and where the currents are when you solve a DC simulation, you can easily do that in an intuitive way rather than trying to hack around to make that happen. So it's an open source project. It's MIT licensed, so you're free to use it, do what you like with it. There's 2 papers about it. There's links in some of the slides from yesterday. So there's one paper describing the overall simulation framework, and then there's one paper specific to electromagnetics. And that also breaks down how we're thinking about the forward problem and how we've structured that. Let's see. Okay, a couple of important things to point out for you. Let's go to the documentation. So there's 2 ways that you can really get in touch right now. We have a Google form, and I'm trying to see where the info is. There is a link for that, but I think it's on the README somewhere. We also have Slack, and so that is one way that you can get in touch with us and have a conversation. And so that you can actually, if you've got questions or things like that that come up, you can get in touch with a real person, and that's always helpful. The one place to start is really looking at the examples. So there's a whole suite of different examples, everything from some that have been published. So these are the ones from the EM paper. So if you want to go in and reproduce any of those figures, these are the scripts that we use to generate them. These ones, it's not a bad place to start, but it's also, there's a lot of plotting code and it's a little dense because of that to make the figures publication quality. So in a lot of ways, I would actually recommend starting with some of these ones below. So we've got a couple examples showing a linear inverse problem, examples showing how to build up different types of meshes, examples for gravity and magnetics. So we saw a lot of gravity and magnetic data being shown today. And so if you wanted to actually see how you can go and invert those in 3D, these are a couple examples that will show you how to do that. And this one in particular is actually a field data set. So there's a couple examples with DC, frequency domain EM, natural source, time domain. There's fluid flow, if you're looking to do like Betos zone. We've got Richard's equation in there. There's a little bit of seismic, it's just straight ray tomography. So if that's something you're interested in and interested in contributing, that would be fantastic and we could get in touch. And then a couple of utilities. So what I will do is actually show you now the MT tutorial and what's involved in that. So there's actually 5 notebooks associated with it. 2, we've called them sort of appendices because they show a lot of the gory details of building up your sensitivities, how to actually test that. So it's really, really dense. But if you're interested in seeing how that's done, all the details are there. So in the first notebook, so I'm just going to go ahead and clone this again so that I can run it from Doug's computer. And then we'll go ahead and run this. So in this first notebook here, what we're going to do is actually build up the discretization for the 1D MT problem. And so I'm not actually going to go through and run this, but I'll just give you a quick overview of what's in there. And please stop me if you have questions or there's something that you would like to see a little more on. Okay. So we walk through, starting from Maxwell's equation, what is the system that we're going to actually discretize and solve? Because we're in 1D, we can take advantage of that symmetry and really reduce this down. I'll show you where things are discretized. So what is a node, what's an edge, what's a face in this case? So how do you represent a vector in a discrete world? And then here we actually show you what the discretized system should look like. And then below, we'll build that up in SimPeg. So we design a mesh, get our operators, and then we're going to go ahead and build up that system. So here we're just defining a bunch of parameters. I'll skip through that. But then this is the system that we want to solve. So we then go ahead and show, okay, these are all the operators that we need to build up. So we need our gradient, we need our sigma hat matrix, our divergence, and then our boundary conditions to give us the right-hand side. So we build all of those, and then can just assemble the matrix, and then go ahead and solve. And so a couple, the last thing that we show here is just a comparison with an analytic to check that we've done this properly. So that's all the first notebook does, is just derives and shows you how to set that up and solve the 1DMT problem. So the second notebook, what we do is we're going to build on that first one. So we're going to assume that we can solve the 1DMT problem and look at a couple important choices in setting up a forward simulation. So I will walk through this briefly. I won't go through all the details, but I'll show you a few things. So first off, what we're doing is we're installing SimPeg and PyMat Solver, which is a wrapper to help access lower level solvers like MUMPS or Cardiso. Can you guys see that okay? Is that big enough? Yeah. So then here we import a bunch of standard Python packages. So if you're familiar with MATLAB, NumPy basically is like MATLAB. It does all the matrix calculations. SciPy_sparse does sparse matrices. Matplotlib does all the nice plotting. And then there's a few things like parameters that we're going to import from SciPy. And then this here, what we're going to do with this MT forward simulation, that's the code that we wrote in the last notebook. So that's our script that runs the 1D MT problem. So all we're going to do here is set up a half-space model. And the thing that we're going to look at is mesh design. So we're going to compare what goes on if we make our finest cells too big, or if we don't pad far enough. So one of the things that's really important to consider when you're designing a mesh is that we're capturing the highest frequencies properly. So the rapid changes near surface, we need to make sure that our finest cells are fine enough to capture that. So the thing to look at there is the skin depth. And so our sort of rule of thumb is you want to make sure at least 4 cells for your smallest skin depth. And then you need to also make sure that your mesh extends far enough, because the boundary condition on the bottom basically says we're assuming that our fields have decayed. And so you need to make sure that you're a couple of skin depths past your lowest frequency. And so here all we do is based on our 100 ohm meter half space and the frequency ranges that we've chosen, we print out our skin depths, and we're going to design a mesh to make sure that our finest cells are fine enough and our mesh extends far enough. So we can go ahead and build up a mesh. So all we're doing here is defining our number of cells, how thick they are, and then in this case we use a logarithmically, or like an expanding mesh. It's a tensor mesh. And so we can see that the mesh extends here now for 40 kilometers, and we needed to make sure we went at least this far. So we're good to go there. Okay, and so to make this a little more interesting, let's add a layer. So we're going to add a conductive target partway down, and then we're going to go ahead and compare with an analytic. And so what we'll do here is we're actually going to plot them both. So first, let's just make sure that, if we've done a good job defining our mesh, as we think we have, are we matching the analytic? And so in this case, we're doing a good job in both apparent resistivity and phase. But one of the things that you might want to look at is, okay, how far can we push that? So what we've done in this notebook is there is a couple widgets here where we can play with the minimum cell size and the domain extent. So right now, our minimum cell size is 125 meters. So where on these curves do you think we're going to start to break down if I make those cells thicker? What's going to happen? So we have high frequencies here and low frequencies here. Yeah, and so because our minimum cell size is really defined by the highest frequencies, you can see as I start to increase that, we're peeling off the solution up here at those highest frequencies. So that kind of shows you what happens when you're improperly designing your mesh. I can actually introduce numerical noise just because of your mesh. Okay, so if we make that back down to what we were expecting, now what happens on the other side? What happens if we reduce how far our domain extends? Or even break down? Higher. Perfect. So again, you can see it peeling off here at our low frequencies because we've told our simulation, the field should have decayed by now, but we're actually still getting energy down there. So again, we've introduced numeric noise. So this is just a simple way to calibrate your understanding of what's going on with this forward simulation and how do you actually design the mesh. One of the other important things to consider before we actually even move to an inversion is what are your expectations? What can we actually reasonably expect to get out of an inversion? And so one of the classic examples of a challenge to inversion is non-uniqueness. And so what this is basically there are several different models that can fit our data, but there's only one Earth model. And so in this case, the classic example for NT is the non-uniqueness due to the conductivity thickness product of a thin layer. So if we set up an example here where we have 5 different models, all with the same conductivity thickness product, we can simulate now our 1D MT solution and see that, okay, in all of them, we see that there is a conductor layer. So we're confident that there is a conductor down there. But there is a lot of similarity between those data sets. And if we go one step further and we add a little bit of noise, you see that it would be extremely difficult to actually try and tease apart which model we actually have from the inversion. And so this is where bringing in things like a priori information is really important. If you know how deep your layer is or how thick your layer is, or perhaps how conductive your layer should be, those pieces of information can then actually help specify which model should we be looking for. So that's the end of this notebook. Are there any questions? No? Okay, so then the last one that I want to show you is a 5-layer inversion. So what we're going to do here is we're going to assume that we've got our forward modeling, we know how to properly set up a mesh, and we've calibrated a few of our expectations about what we can get out of an inversion. And so here we again bring in the packages that we need. The way that we set up the inverse problem is as an optimization. So this is a fairly typical Tikhonov style version. There's two pieces here. So there's our data misfit, which is this 5D. And then there's our model regularization, which we call phi-m. And then in between them, there's a trade-off parameter. Basically what that does is says how much do I care about my model regularization versus my data. So if beta is really, really big, you're saying pay a lot of attention to my regularization. If beta is smaller, then you're saying fit my data really, really well. And so for this example, we'll use just simple L2 norms. What's nice about these is they're easy to differentiate, and they're also convex and stable, so it's a nice place to start. And so what our data misfit is here, we incorporate a noise model through our W matrix. So we say, you know, how well should I trust, how much should I trust each of my data points? And we usually use some percentage of the data plus a floor to make sure that, you know, if there's zero crossings, we're not trying to really, really fit zero. This guy, this F of M, that's our forward simulated data, and then this is our observed data. So we're going to try and fit our data. And then the regularization is important because of this non-uniqueness. And so when you have something that's non-unique, that means we can't just solve for this guy. That's not a stable problem, right? There's many, many solutions that can fit our data. And so the regularization puts some constraints on what we actually expect for a model. And so one of the classic places to start is a smooth inversion. And so we define a Tikhonov style regularization that has two parts. And so the first part is basically these, we call it the smallness term. And really it's a measure of how close we are to a reference model. So if we've got, often this is just a half space. So we'll say, you know, I expect my background to be about 100 ohmmeters. So let's try and keep sort of in that range. And then this alpha term basically says, how much should I pay attention to that? Then there's also a smoothness term. And so this basically penalizes a gradient. So it says, don't create large jumps in my model. And then this alpha Z weights that. And so it says, how important is getting a smooth model out? So as you can see, just by looking at this, there's a lot of different tuning parameters in here. And so the goal of this example is to go in and play with those and tinker with them so you can see what happens. So I'm going through this pretty quickly, but all we're going to do is set up a model. So we're defining some layer tops and some resistivities for those layers. We'll define where our receiver is, what frequencies we're going to use. Here we set up our receiver object, which has a location and it knows which frequencies it's listening to. Here we set up a mesh. So as we said before, we want to make sure that it goes far enough. And so this little utility basically builds us a mesh that is reasonable for this MT model. And SymPeg is written in Python, which is an object-oriented language. And so what that means is you can create an object like a mesh, and it actually has methods. And it has properties. So we can look at, for example, how many cells are in our mesh. So in this case, there's 64. Also, because once the geometry is defined, we actually have all of our differential operators. You can get things like the phase divergence and all of that. So you have all of the differential operators once you've defined your geometry. And then another thing you can do is go ahead and plot your mesh, because we want to have a look at it, make sure it goes far enough, see where our cells are and where our phases are. So this is the model we're going to try and work with. So it's 5 layers. We start with and we're plotting conductivity here. So it's a resistive top, then it gets a bit more conductive, and another resistive layer, more conductive, and then a little more resistive. So the first thing we're going to do is simulate some observed data. So we've got our true model and our true data, and then we'll add some noise to those data. And so we can go ahead and plot and see what our, our original true clean data are and what our noisy data look like. This goes into a lot of details, so I'm not going to go into that now, but it is included in the write-up here, and you're welcome to get in touch with us with questions. And so this is the SimPeg framework, the setup, and how we really are thinking about the inverse problem. And so what I mentioned before, these inversion elements, that's really what we're going to focus on in this example, is the data misfit and the regularization. So all we've written here is a simple function to actually go ahead and run the MT inversion. So this is a lot of inputs, but these are all different things that you can play with in the inversion. And so we walked through playing with a couple parameters, but we've tried to set it up so that you can go in and tinker with everything. So there's things like the reference model. So what I mentioned before when we're trying to define that smallness term, how close do we want to be to our reference model? That's where you can plug that in. How much do we want to weight the smallness versus the smoothness terms? What should our beta be, which is that trade-off parameter between the regularization and the data misfit? And then if we want to actually change beta during the inversion, we can do that as well. Yeah, so we went into some details here on that. So in this case, we're going to start with a hash space, and we're going to also use that as our reference model. And we're going to start with favoring a bit of a smoother inversion, so our alpha z is bigger than our alpha s. And we will, and we're gonna cool beta so that you can go ahead and look what happens at each iteration when we're changing the trade-off parameter between these two terms. So there's a few things that it prints out. So we print out the value of beta, we print out the phi d, so what's our data misfit, and the regularization. And so then in this case, once the inversion is finished, we can plot out our Tikhonov curves. And so in this case, what we're going to do is we're going to show we've got phi d, phi m, and then phi d versus phi m. So this is with beta here. And what we've marked as the star here, that's the target misfit. And so that is defined based on your number of data. And so if you've defined your noise model properly, your target misfit should be close to, your phi d should be close to your number of data. And so here, one of the things that we want to do is actually go ahead and look and see what happens if we pick somewhere on the curve that is a smaller beta and somewhere on the curve that's a larger beta. So let's see what happens with that trade-off parameter. What does it look like to underfit versus overfit our data? Okay, so starting at iteration 0, we started with our hash space, as you expect. And so, so as we scroll along, you can see that a bit of structure starts to get introduced into our model. And so let's, for example, see, okay, so right here where we are, we've picked beta is 50. So we've got, right now, we are doing a better job fitting our phi m than our phi. And so there's a few things that you can tell. There's a little bit of information that we still have in our data that we can try and pull out. And our model is still pretty smooth. So this is an example of being underfit. If we go on the other side, what do you think the model will look like? So here, just like this. So if we go too far, then what happens is we're actually trying to fit our data really, really well. And so in order to do that, the inversion can just keep introducing structure. And it'll keep doing that until we fit all of these little wiggles in our data. And that's no good because we've now introduced what looks like an extra layer in here. We're overshooting and undershooting our resistivities. And so that is the danger of overfitting. And so in this case, if we actually go back and see, as we get closer to our target misfit, which is in this case 9 iterations, we see we can do a pretty good job recovering 5 layers. You see that there's 5 different layers. We're doing a reasonable job of showing where those are, and doing a reasonable job of fitting our data. And so it's not always that exactly iteration 9 is the model, right? In some cases, you need to be looking around that target misfit. You need to have an understanding of what your data misfit are. But it's important to keep in mind the dangers of over versus underfit data.
You define the target misfit, huh?
Yes, based on the noise model that we introduced. Yeah. So if you've properly defined your noise model, then the target misfit is well defined. But of course, that is again a choice, and so it's important to look around that curve and like interpret it within the context of geology.
So you don't use this L-curve criterion. So this red star, the target misfit is right where the L-curve is ending, right? This could also be a criterion if you have no information on the noise.
Yes, exactly.
And actually, very often we use that because we don't have a very good idea of what the noise is. Okay, so you at least want to describe a relative error for the noise, and then some absolute error you might adjust just based on the L curve. Or you can use the DCB, lots of opportunities. Thanks.
Yeah, so there's a lot of different ways to define, what's the inversion model that we should choose.
But I think in that regard, always you need to look at a number of solutions and try to put your subjective input into that as to what seems geologically sensible. So there is some personal input.
So the last thing that we show in this example is tuning the alpha S and the alpha Z. So what happens if we make alpha S really, really large, try and make a small model? What do you expect that inversion result to look like? That's just one example. Well, let's maybe start the other way. Okay, what happens if you expect what happens if you define an alpha Z that's really, really large? So that's the parameter that's controlling the volume, how important your smoothness is.
Yeah. You will get a very smooth model.
Exactly.
And the very big alpha S will give you a very flat model, like very close to the reference.
Let's take a look. So in this case, we're running 2 different inversions. So one where we make alpha S very small, we've got a large alpha Z. And then one where we make alpha S very large, and we've got a very small alpha Z. And so we'll call the one with the large alpha S, that's our small inversion. And then we'll plot both of those up, along with the one that we showed. Yeah, we'll plot both of those up. So here, the blue one is our smooth inversion, and the orange one is our small inversion. So it actually, what we've done in the small inversion is, we've allowed now large jumps in the gradient. And so it is actually, you're right, it is going to try and keep values close to 100, But in order to do that, it's going to throw other values up and down to actually fit the structure in the data. So you can end up with a really choppy model if you turn that out. So are there any questions with that? I know that was a fairly quick overview. Okay. I think yeah, go ahead.
Can we have an even larger of
Even larger, what? Which one?
Alpha S in a small version?
Sure. How large?
100 times.
Okay, so I think we've run these just for 13. Yeah, so it's again pretty choppy. We've sort of saturated it. So the difference between 5 orders of magnitude and 7 orders of magnitude at this point is like not too big.
We have the reference model.
We do. Yeah, the reference model is it is 100 ohm meters. Yeah.
And so you can see at the back end, where you don't have any resolution, it's gone back to the reference model.
Where you don't fit any data.
Yeah, doesn't matter what you put there, it's not going to affect the data. So that's just your a priori information. Actually, if I make one comment here, that's actually a good way to find, people are always worried about depth of investigation, right? So that one way of doing that is to actually change your reference model, okay? And you run it with 2 different reference models, then you look at the back end, and that smallest term will take it down to that reference model. And when it does that, you know that you're just controlled by your regularization, nothing with respect to the data. So that's at least one way of kind of getting some sense of how deep your survey is.
Yeah, okay, so I think we're getting close to wrapping up here. The last thing I just wanted to point out is there's a couple examples, again, as I said earlier, there's this frequency domain one and the time domain one. And so these will actually show you if you want to run forward simulations using SimPeg for electromagnetics in frequency or in time. These are good ones to look at, and they will actually show you some of the figures that you saw yesterday. And then again, for using SimPeg to get in touch, there is, I forget where the link for the, there's a link for Slack, and you're welcome to join and ping with questions. We also have a Google form, and that can be accessed, I know, from where the code is. So there's a Google form right here. So both of those are ways to get in touch. Okay, well, with that, if there's no more questions, thanks everyone for sticking with us for 2 days. And thanks again for everybody's presentations today. I certainly enjoyed hearing what everyone's up to.
Yes, I'll just echo that. We're actually hoping that this is actually going to be a start of a longer communication, and some people have already offered to contribute to GeoSci. Tell us what IP membrane polarization is. This is good, and yeah, maybe we can use Dieter's program and wrap it up in some apps and make that useful too. So anyway, it's been really good to get an insight as to what the problems are, and again, really thank you for putting together the presentations, and yeah, you can be able to view them on our website soon. So, thanks, guys.
Thanks, Ray.